today I will be talking about calculus and algebra with symbolic arrays. Mathematica 14.1 introduced new functionality for computation with symbolic arrays. It includes symbolic representation of arrays, computation of derivatives of array functions with respect to symbolic array variables, as well as support for array variables in several symbolic computation functions. The upcoming release of Mathematica will add functionality for transforming and simplifying symbolic array expressions, and will extend support for array variables to more functions. In my talk, I will discuss the new and upcoming symbolic array functionality and show some examples. So let's give an introduction to the talk. So first, non-threadable attribute. So we have a new attribute that prevents threading of listable functions. Is given to symbols that may be used to construct expressions that represent arrays. So let's look at what functions. Got, for instance, adjugate is a function that produces arrays, so it has the attribute. And so this is a collection of built-in functions that have the attributes. We have introduced three objects for representing symbolic array variables. It's vector symbol, matrix symbol, and array symbol. We have also introduced four special array objects. It's a symbolic zero array, so it's array of zeros. Symbolic ones arrays, it's an array of ones. Symbolic identity array, it's the array you get when you differentiate an array variable with respect to itself. And symbolic delta product array, it's a generalization of symbolic identity array. It's also a special array of zeros and ones. Now, symbolic array calculus. So D was extended to work with symbolic array functions and variables, and I will talk about this. And the upcoming version of Mathematica introduces symbolic array transformations, array expand, array simplify, and component expand. And it also extends tensors expand and tensor reduce to work with the newly introduced symbolic array objects. So first, let's talk about symbolic array variables and threading. So a long-standing difficulty with using symbolic vector, matrix, and array variables was that evaluation of arithmetic operations treated symbolic expressions as scalars and threaded them into list arguments. So for instance, if we add x to vector 1, 2, then x gets added to each component. So this is correct if x is a scalar. It's not correct if x is a vector or an array. So for instance, if we would like to set up a convex optimization constraint a dot x plus b vector greater or equal than 0, but because of threading, we could not do it directly because our vector variable, intended vector variable x gets threaded into the vector here. So the documentation of convex optimization suggests using inactive plus, and this was one way of doing it. So if we do inactive plus, then plus doesn't thread, and we get the intended constraint, and convex optimization was working, but it was not very elegant to have to use inactive plus like that. So in Mathematica 14.1, we introduce a new non-threadable attribute which specifies that a symbol and expressions that have this symbol as the head should not be threaded into lists. So for instance, if we set attributes of sim non-threadable and we add sim to vector 1, 2, doesn't thread. And also an expression with head sim will not thread into the list. So now most standard built-in functions that produce array results have this attribute. So for instance, if we take inverse of math, which is expected to be a matrix, and add to a matrix, then it doesn't thread inside. So we get the expected arithmetic expression. And in version 14.1, we introduced symbolic array variable representations through vector symbol, matrix symbol, and array symbols. These are new objects that can be used to construct symbolic representations of vector matrices and arrays. For instance, we defined vector symbol of length 2, and that's how it prints, and we get a tooltip saying that it's a vector symbol with dimension 2. And these new objects have non-threadable attributes, so this vector correctly does not thread into an explicit vector. And now we can set up the convex optimization constraint from the last example directly. Now vector v did not thread into the matrix, and we get the correctly set inequality, and we can run convex optimization, and it works. And we can use array variables in other solvers. So let's define a matrix symbol. This is how matrix symbol typesets. And we get the tooltip saying that's a matrix symbol with dimension 2 by 2. And we can use it in solve. And we get the solution for the matrix. And let's define an array symbol. Here is how it typesets with the depth of the array printed above the symbol. And we get the tooltip saying that it's an array symbol with dimension 2 by 2 by 2. And we can use it in minimize. We get the solution for array. Now let's talk about symbolic array expression. So let's create a symbolic matrix with dimensions m by n. We can use symbolic dimensions. And this constructs a symbolic array expression. So here is new typesetting for transpose and conjugate transpose, and we can compute tensor dimensions of this. So this is a depth 4 array with dimensions mm and n. So now let's create an array of depth 3. Now a minus a will not give 0, it will give a symbolic zeros array, because arithmetic now knows that a is not a scalar, it's an array. So the symbol is symbolic zeros array with dimensions pqr. And if we add 1 to an array of zeros, we get an array of ones. And we have another special array, it's symbolic ones array with dimension pqr. And if we make the dimensions numeric and apply normal, we'll get an explicit array. So here is an array of ones with dimensions 2, 3, and 4. Now, D has been extended to compute array derivatives. So let's say that A is a matrix and V is a vector with symbolic dimension n. So now, since we didn't say anything about x, then x is treated as a scalar for derivative. So this will be vector valued function dot matrix valued function dot vector valued function of a scalar variable. And here is the derivative. So the derivative is a vector. Now let's take the derivative of a vector valued function with respect to a vector variable. And the result is a matrix. In this particular case, the derivative is very simple. It's the matrix we multiplied by. Now let's take the derivative of the same vector valued function with respect to a matrix variable. So now we have somewhat more complicated result. this here is a symbolic identity array n by n dot vector, and this notation is transposed by 1, so the dimensions of the array are rotated by 1 to the right. And tensor dimensions, this is a array of depth 3, because it was a vector valued function with respect to the a matrix variable. So the first dimension corresponds to the values of the function, so it's a vector valued function, and the other 2 dimensions correspond to the variable. So symbolic array of dims is the result of differentiating an array variable with dimension dims with respect to itself. So if we differentiate a matrix with respect to itself, we get identity n, n, and this is a depth 4 array with dimensions n, 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 and n. Now let's take a derivative of slightly more complicated matrix valued function, inverse. So here is the formula for the derivative. It again involves symbolic identity array and transposed this time by rotating dimensions by 2. And now, so vector symbol, matrix symbol, and array symbol also take domain arguments, so we can specify that we have a real vector, and now we can compute derivative of variance. Variance is differentiable only for real vectors, and here is the result. Okay, so let's look at chain rule for array functions of array variables. So we have F is a matrix symbol, G is an array symbol of depth 3, and V is vector symbol. So let's compute the derivative of composition of symbolic array valued functions with respect to vector variables variable in this case. So the result looks quite similar to the regular chain rule for scalar objects, except that we have this dot with 3 underneath. So that's an array dot. It's a new function. So let's look at what it is. So it's had this array dot. First argument is the derivative f evaluated at g. Second argument is the derivative of g evaluated at v. And the third argument is shows how many dimensions of those 2 arguments have to be dotted together. So array dot of a, b, k computes the product of arrays a and b obtained by summing up products of terms over the last k dimensions of a and the first k dimensions of b. So if we look at dimensions of the first argument, so this is a matrix valued function of an depth 3 array argument. So it will be depth 5 array. First 2 dimensions correspond to the dimensions of the result, and last 3 dimensions are dimensions of the variable. Then some dimensions of the second object. So its first 3 dimensions correspond to the dimensions of g, and the last dimension corresponds to the dimension of vector v. And now we are summing up with respect to the last 3 dimensions of the first argument and first 3 dimensions of the second argument. So what's left is first 2 dimensions of the first argument and the last dimension of the second argument. So as an example, let's look at Taylor approximation. So we will find the first 3 terms of this Taylor series of inverse of A. So it's a matrix valued function of matrix argument at C equals identity matrix. So the first term in Taylor series is f of c, just like in the scalar case. Now we have inverse of identity matrix, doesn't simplify automatically. We have a new function array simplify coming in the next version. So let's simplify this. So it's an identity matrix. Now the second term again looks very much like in the regular Taylor series formula. It's a first derivative evaluated at c dot a minus c, and the dot is array dot with dimension 2 because we have function of array of matrix argument. So let's compute the derivative. Now we compute array dot. We again we simplify this derivative, and array dot with a minus c, array dot of degree 2. Here is the formula, and the third term is again similar to regular Taylor series, 1/2 of second derivative, that instead of a minus c square, we twice do array dot with a minus c. So compute the derivative. Then again one more new formatting of transpose, where it's a transpose with permutation. And we do the array dots and we simplify the derivative. So we get somewhat smaller formula, still looking a bit complicated, but it's much smaller than it was. So now let's compare order 0, 1, and 2 Taylor approximations for, now we have to take specific n equals 7, and we generate some matrix with random entries within 10 to the minus 10th of entries of the identity matrix. So generate the random matrix. First order approximation gives us approximation up to 10 to the minus 10. Second order approximation gives us approximation up to order 10 to minus 20. And third order approximation is good up to about 10 to minus 30. So we see that indeed we are getting better approximation of the result. Now let's talk about array expand. So upcoming version of Mathematica will contain a new function array expand, which expands out symbolic array operations. The function makes use of multilinearity of array operation, as well as numerous array, matrix, and vector operation identities. Let's clear the symbols, and here array expand of a plus b dot c plus d. So we don't really have to specify what a, b, c, and d are. Array expand will assume that they are appropriate arguments for the function they are used in. So for the function dot, and uses linearity of dot to get this result. Here we want to specify that S and T are scalars. We do it by saying S and T are elements of complex numbers, and we get linearity of trace. Now we do array expand of inverse of a dot b, but now a and b are specified to be matrix symbols with dimensions n by n. And we actually had to do it here because if we just had symbols a and b, even if they were appropriate for the functions they are used in, they could have been rectangular matrices that as a product give square matrix that has an inverse. So we really have to say that they are both square matrices, and then we can expand it. Here we can say that A, B, and C are matrices using an assumption. And finally, we apply array expand to determinant of 3 times matrix symbols with dimensions n by n. Again, matrix symbol was needed here because now we know what the dimension is, so we can pull out 3 to the nth. And here we do array expand of dot product of cross products. And we don't need any assumptions, because if those arguments are used in cross, they have to be, in 3 arguments cross, they have to be dimension 4 vectors. So as an example, let's derive a formula for the gradient of the least squares cost function. It's an example from Mathematica Stack Exchange post, where the author wanted to derive a formula that was given in an online lecture. So now we can do it. We can derive this formula directly. Just specify matrix symbol to vector symbols. The cost function is given by this formula. We can compute the gradient of this formula, and we can simplify the gradient. And the result is exactly the formula that was given in the online lecture. And finally, let's talk about component expand function. So component expand expands out symbolic array expressions in terms of index components. So we take a vector symbol with numeric dimension, we get explicit vector of indexed components. We can specify dimensions through assumptions, and that expands determinant of A dot B. Here we can expand a vector inequality in terms of inequalities of components. And finally, we can use symbolic once array, and it will be automatically converted into appropriate components. So we get this dot product expanded in terms of components. So this was the last slide. Thank you for listening. Okay, hello. Let me now answer the questions that I see in the Q&A. Actually, I see here one question. So are the parentheses around the term containing only a single vector strictly necessary? So as far as I understand it, it's something that typesetting does. It's conservative. So since the vector symbol is typeset as an expression with an overscript, then if we have a subscript or superscript to this vector symbol, then the typesetting puts the parentheses around the vector symbols just to indicate, what the superscript and subscript is to the whole expression with the overscript arrow over it. So that's how it works. It's typesetting being conservative, basically. Is this notation, vector, etc., explained in Wolfram language documentation now? Yes, it is. That was introduced in version 14.1, so it is. Will it work with array reshape? Nope. So array reshape was not currently. It was not used as one of the array transformations. It may be added in future, so the future versions may work with array reshape. Right now, array reshape is not treated as symbolic transformation, and it actually will give error messages if you give something that's symbolic as an input. So the next question is, how would array components and other function named array will be affected? So we introduced several functions that have array in the name. Other functions that are there, they're not necessarily will work with symbolic array. So let's see what array components is. Yeah, so it looks like array components is purely structural function, so it's not really going to be used in symbolic array computations. Can tensor contract of tensor product be array reduced into dots? I don't think it currently can, but it could be possibly. So that's a good suggestion, that to analyze tensor contract expressions and try to reduce them into dot products when they actually represent the dot product. So Alex asks whether we can or cannot evaluate n-dimensional integrals. Well, we can evaluate some n-dimensional integrals, like n-dimensional integrals over regions, and you can use array variables in integrate or vector variables in integrate. But for as far as n-dimensional integrals go, we have not introduced any new functionality. Okay, so now there is some specification to the question. So functions that have array in the name. So how do we tell whether they can be used with symbolic arrays or not? So, well, one way of telling it, you would really have to think about whether the function seems to be doing something structural and complains when you give it symbolic input or not. So if the function is supposed to do something specific to explicit arrays, then probably it's not going to be used in the symbolic as a symbolic input. Although it actually does change. So some of the function can be probably changed so that they could be used in symbolic arrays. So it's still work in progress, and some functions may go from being purely structural to being functions that can be used in symbolic arrays. The one thing where the function is completely structural and cannot be ever used in symbolic expression if the function does something to the expression with arbitrary heads. Then it's not really good for symbolic use. If the function right now does something with explicit arrays only, but not with expression with arbitrary heads, then it possibly might be used as symbolic array computation functions in the future. Oh, I see the question that has been moved to the top. Okay, so I'm thinking notes in Mathematica. Why does the spell checker mark the Vendira, Kapadria, and Julia Alexandrini, but not Adam Szczepański? No idea. How does spell checker mark them? Oh, interesting. So it seems my last name is being recognized by the spell checker. That's nice. Yes, probably. I don't see any more questions, so let's end the stream then. It says submission is closing in 8 minutes, but I don't see any more questions, so let's close it. And thank you very much.